Alright, so this week I will get into threads and fasteners. Yeah, we'll see what we do with the fasteners and threads, alright, in our drawing. And also, we're gonna study how to calculate bolt and screw clearance holes. So again, symbols, 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 that's what we use in engineering drawing, yeah? It's not regular artistic or realistic drawing. We will use the symbols to represent fasteners and threads. Okay, this is just a review. So your fasteners, you have bolts and nuts, we have set screws, we have washers, we have keys, and we have pins. So these are all your fasteners that you need to know when we do our drawings. Of course, the fasteners are just a temporary joining the two parts together. Okay, they're not permanent means to join or mate the parts like welding or some strong adhesives. Okay, so there are many ways of joining. So joining methods, one of the methods is to use the fasteners. Yeah. And of course, welding is another type of joining method, and adhesive is the other type of joining method between the two parts. And depends on the product, you're gonna choose appropriate joining method to join the parts. Of course, we always do what we do best. So we have to draw, and then all the features that we draw, fasteners and threads, of features in our engineering drawing, so you definitely need to define them or specify them. So what are we gonna do for the threads or threaded features? We're gonna put it in a thread node. Yeah, for fasteners, general ones, we're gonna put them in the standard part sheets. Okay, so that way they can be able to do their purchasing, which is order them, whatever you need to do the manufacturing. Because purchasing is another job that you might want to look into. It's a very easy job. All you have to do is taking in the order information, schedule for purchasing, usually done through the network. There's a financial part in it, so the people with the financial degrees, they usually do that. A long time ago, all works related to engineering are done by the engineers. Nowadays, it's different because technology evolved, and also there's a big competition between who is getting the jobs between groups. So so many people come in and take away the jobs from the engineers. I don't know it's a good thing or bad thing, but then since all different backgrounds come into the field, there is an issue with the titles, and also there are also issue with the understanding of the same thing, because they understand in different ways, other than engineers, because the study lines are different, so the way that they think is also different. So I don't know, that's a good thing or bad thing, but this is a world, current world that you're in, so you just have to learn how to be okay with different people from different backgrounds, and also from different study, or different majors, coming into the same field, talking different things, and it's a headache to deal with them every day at work. Okay, I just want to teach you now so you are mentally and also physically prepared for it. Okay. Alright, screw thread. I'm going to start our definitions. These are just formal definitions. You can put it in your own word when you try to understand them. Yeah. So screw threads usually you can see them. Yeah. When you go to Lowe's or Home Depot, Tractor Supply Store, Ace, you're gonna see all the screw, and then you can take a look at very carefully the threads on the screw, and you will see they're usually helix. Yeah. So we have internal and external thread. The very first one is the external thread. Of course, we call it external because the threads are on the outside. Yeah. And if you look at the screw very carefully, you're gonna see the chamfer. Yeah. That's why in our drawing app application, you can see how to make the chamfer at the end of the screw. Yeah. So functionally it's really good because it makes it easier to engage the nut. So machining, we make the external thread. Yeah, use a die or a lathe machine, or sometimes you can do it manually. A long time ago. Another type threading, internal threading, is the internal thread you can see, of course, inside of the member. Okay, so if you look at this, you can see the threads is internal inside. Machining, we make the internal thread, by making a cut, and you use a tab to do that cut. Alright, so when we study the screw, you're going to see the major diameter. Major meaning is the largest, diameter symbol. You will see a big D as in dire, meaning diameter, abbreviated word right here. And this symbol is for both internal and also external threads. Okay. Again, symbol very important. Every time you see D, you know that we're talking about major diameter. Minor diameter, little d. See that? Minor, of course, your smallest diameter, on your screw. Your thread, the depth means how long, your threading is going to be major minus minor diameter, okay, divided by 2. That's just a general definition, okay. So the thread usually you of course this length is a measure from the top of the crest of the thread all the way down to to the beginning of that minor diameter. So major diameter minus minor diameter. So you're going to get that difference little material for that thread, and then divide that with 2. So if you go back here, see you have a major diameter and then the minor diameter, so you can see the thread. So we're talking about this little length right there as the depth of the thread. Okay, you can also see right there the same thing. Since this is a 3D picture, it's a little bit difficult to see, but you got the idea of that. And then pitch is dp. Okay, so that's the diameter and that's the pitch, so therefore we call it pitch diameter. Pitch is kind of a little bit difficult for you to be able to see, but it's just a diameter. Alright, it cuts your space and threads equally. So when you take a look at it, we're talking about these. See that? So each one of them. So you have space and you have thread, space, thread, space, thread. And of course, when you machine it, it cuts the line all very equally. And we call that pitch of the screw or pitch of any fasteners. Crest is easy, like your little mountain. The top of the surface, the root is where the valley, like the little valley between the 2 crests, like the bottom surface. And then of course the side is the surface between your crest and also the root. So you have So you have like that, yeah. So the crest, then here that's your root. The bottom, the side is the surface, yeah, between the crest and then the root. So here this is the root and that is the crest, and this one is your side, yeah. All right, the not the pitch diameter, just the diameter, just the pitch itself is the distance, and that distance is measured from a point on a screw thread to a corresponding point on the next thread. So it's kind of like in between the two crests, yeah. So they route it here like in threads, in between the two threads. So that's your pitch. International students are like, I noticed they have issue understanding pitch. I don't know why. It's pretty okay, yeah. It's just between the two crests, yeah. And so yeah, try to get that. You have you're okay with everything except the pitch thing, yeah. So I want you to concentrate between the crest and root, and you're gonna get the pitch anyway, yeah. All right, so that's your hint. Then we come into angle. Angle is, of course, so we're measuring the angle between the threads. So where are the threads? The threads are the one that the helix, yeah, the helical surfaces that you see on the fastener or screw, or yeah, we have external and internal thread like that. So the angle is in between them, okay, and of course depends on how many numbers of thread you have on the fastener, the angles are there, yeah, and that angle got to be the same, yeah, when you machine. Axis is very easy because you have a diameter, so therefore the center, the longitudinal line, center line, yeah, your axis is going to be a screw axis. And lead is the distance, another distance. It's just a distance that you go one, yeah, helix up. So every thread you go one helix up, 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 all the way to the end of the threading feature in your fastener, and we call one turn of that distance, one turn of the helical, or one turn of the thread axially, okay, and we call that a lead. This is easy for you. You've been doing this all the time. Your right-handed thread, and then your left hand. If you go right hand, then it's go right hand, which is your counter, yeah, which is sorry clockwise, and this one is the left hand is your counterclockwise. Because I'm saying at the rate my brain is thinking. Sometimes I'm like thinking here and the same. So anyways, the right hand is a clockwise, and then your left hand is your counterclockwise. And then of course we come into exercise number 1, and so here you can see a bolt, yeah, it's one type of fasteners, and you can see the head here, yeah, this is just a middle body right there, mid body, and then of course this is where your threads are. So the right pedal on a bicycle. So if you think about your bicycle, yeah, this exercise is giving you a thread like this, and then making you, yeah, think, okay, think about the bicycle and think about the right pedal on a bicycle. What is it, yeah? Is it left-handed or is it right-handed? So you think about left hand, right hand is with a counterclockwise or clockwise, yeah? So right hand is clockwise, so bicycle pedaling, right is right-handed, which is you're pedaling clockwise direction, yeah? Therefore it's R for right-handed. And left pedal, of course, is going to be counterclockwise, so therefore left-handed. Propane fitting, I'll have to show you. So it looks like this, okay? So propane fitting, you can see that, and that's actually is a left-handed, okay, threading. It's a little bit difficult for you to be able to see it. They all look alike, okay, even though that's like a right hand, or left hand. So you've got to look very carefully where the starting point of the thread is, okay, and put it like front, all right, front view to right to your eye's side, and take a look at whether it's going counterclockwise or clockwise. Okay, if that's counterclockwise, that's a left, and then if that's going clockwise, then it's going to be your right-handed thread. Okay, so make sure you face this bottom surface to your eyesight. Okay, so that way you can be able to see the threads. How is it going, either clockwise or counterclockwise? Then we get into another exercise. This I believe in your textbook as well. So when we study, this one is looks like yes, a screw looks like. So here A is a thread axis, because see that center line right there, and your B, see this little crest right here, and going from the point, one point to the other, and that's your pitch. Okay, then of course the top of this, or like a little mountain top, is your crest. The bottom, like the valley, is your root. And then the diameter E, okay, actually this one is not diameter, it's just showing you the depth. Okay, so it's going like from here all the way to here. So from here, all the way that they draw this E is a little bit deviating. Anyway, so this is your thread depth. I was right. Okay, and then of course, so this F is going to be minor, diameter right here, because it's going from root to root, and of course, if then from here to here, see that's your pitch diameter. Okay. So that's the line between the crest and the roof. See between the crest and the roof, and the root, and that's the line from this line to here is your pitch diameter. Okay, the one that is a little bit difficult to see. Then of course your H is your major diameter. And then we have angle, thread angle right there, sorry, right here, and then this is just showing you the site. This is supposed to be right here, so that way you can see a little bit better. I thought, like, okay, so anyways, the I is your thread angle here. So the only thing that's going to make you a little bit difficult to see is the depth, which is this guy right there, E, because the way that they show it's kind of like a little bit, I would put another, because it's kind of look like a major diameter, I would put probably around here instead of there, so that way you can be able to see the depth of the thread. Thread form, we have many different types of thread forms. Form is nothing but just a shape, how the thread looks like, so we have unified and metric. So let's take a look at each one of them. Okay, so when we deal with the thread form, you have to choose in your design. So before the engineer design, their the fastener, they think about, okay, what it will be used, and then they think about the length of engagement and the load that it's going to carry, things like that. And this is just a strength that your fastener can be able to provide when it is used to join the parts. So we call it this a physics part, or mechanic part, to be able to withstand the environmental forces. You gotta think about all of it. These are all engineering aspects, and then they're gonna do the design, and then it's gonna come to you, and you, of course, you draft it. So anyways, the thread form depends on all these factors when you choose which one to go, either uniform, unified, or matrix. Okay, so here we can see unified, matrix. Of course, there are three others added in the table for you, even though we concentrate this two in this textbook. So we also have square, ACME, and the buttress. Unify, we deal with general use, matrix general use, a square ID thread for your power transmission. ACME, we're gonna use it, because it's stronger. So you're gonna use it to join the bigger parts. And this type is stronger than that. Okay. And the last one is designed to handle very, very heavy forces in one direction, like your truck jack. See? So these are the thread forms. Different, each one of them is different. So it depends on the shape, okay? Depends on the thread form. You're producing different forces to be able to withstand external forces, okay, subjected to that part that you are building. Okay, how are we gonna make them? Internal threads, you're gonna use a tap drill hole, and then you make a tap drill hole, cut it by using a twist drill. And then you're gonna cut the threads, use your tap. Tap is just a tool to make threads, okay? Sometimes you put chamfers, at the end. And again, chamfers are for easy engagement, okay? Because without the chamfer, it's so difficult to thread it and more difficult to use it into any material. External, you're gonna start with a shaft, the same size as your major diameter. And then you're going to cut your threads. What tool are you going to use? You're going to use a die or lathe. So internal, we use a tap, external, die or lathe to make it, okay? Okay, so here you can see the diagram, From here to here is your tap drill. Because you need the internal, so internal thread. This one, of course, the external thread. And here, this is your minor diameter. This one is your thread drill diameter, You're gonna put straight into the part like that. You can see the chamfer right there for easy engagement, And this is just a space. And you use your twist drill point, okay, to make this space. So it's gonna go in smoothly. And from here to here is your thread length. So that's all together 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 in here, This is just a useless, 3 useless threads right there. Because you don't really need it. Just giving more space if you make a mistake here drilling in. So from here to here is your trap drill. Here is showing you the incomplete threads, Your internal threads right here. The trap drill hole, okay, is longer than the length of the thread because we make space for them. I'll show you later. And then the tap drill hole is also a little bit bigger than your minor diameter. Why? The tap drill hole, is diameter is actually bigger than the minor diameter. It's because the external threads, okay, need to fit into the internal threads. So you gotta make the tap drill diameter bigger. So let's go back to, this diameter gotta be bigger than that, because if you make the same thing, it will be very difficult for that to fit into this, okay? So just remember it, like, because it need to fit into, yeah, the internal threads. So the top thread diameter is bigger than your minor diameter. So another one is you have your tab drill hole is longer, yeah, than the thread, and then not the exact. I'll go back to this diagram. Exact, right? Length right there. See, there's some space down there. So that's because you just need space, okay? Space to go for the full length, meaning like she's not writing this here very accurately, and so we always leave some space like that because you're dealing with the metal, okay? Metal usually expand, so if you don't leave the space, it's gonna mess up with the expansion, especially in the yes, when the temperature of your environment increases, okay? So therefore we usually give a little space like that and a little space like that for them to expand, because as like I say, if you have already taken dynamic or static, we we are all materials. Even if humans are biochemical material, these objects are materials. They all come from you have a material list made of all the elements that we know, yeah, so far, and which is your chemistry periodic table right there, and they need space, okay? Because even if we look from the human level, yeah, towards them, it looks like they're all staying together and it doesn't move, but they do, yeah, because they're all being connected temporarily to each other, yeah, physical with attractive forces in between them. So bonding, they are not permanent, okay? Bondings are always loose, so you have to go down to their size, meaning atomic size in there, to be able to understand their world, because we're from the human world, looking at it like a lifeless objects right there, but they're composed of little tiny particles right in there, okay? So therefore we always give the space like that for them to expand when the temperature, increases, because we're all subjected to the environmental forces anyway. That's why we age, and then they go wear and tear, over time. So anyways, let's go back to here and drawing. So we come into screw threads drawing. How are we going to do it? Let's take a look at it. So when we draw, we're going to draw detail. We're going to do it schematically and then a simplified version. 3 ways you can do it. And we're going to follow the ASMEY 14.6, okay? If you get about this much, I'll be very happy. ASMEY 14.5, you should get it by now, 14.6, yeah? If you don't remember, at least if you remember 14, that's cool.
I didn't catch that.
Then we will get into each one of them, So detailed drawing is detailed because you are giving a close approximation, of the appearance of your screw that you're drawing, the actual screw, very close way of drawing, and we call it the detailed representation. Another thing that you need to think, this is just a activity for you to think as you read this material to study initially. So what do you think the pros and cons are, for this type of representation? Doing a detail, meaning like you're drawing as close as your actual screw thread. So think about that. Okay, this I'm gonna make you do this exercise, in class. So I'm not gonna give you the answer right here. It's too easy. I want you to think about it, and at the end of the lecture, you are going to give me the answer. All right. And then let's go and take a look at this external. Already external outside, and the internal is inside. It's a little bit difficult for you to see because it looks like the same as that, but there's a hole right there. So when you see the internal, it's different from this. Of course, when we draw it in a two-dimensional way on two axes, it's pretty difficult. for you to be able to see the opening right here. There is a hole right here. Yeah. Okay. Another representation or another type of drawing is schematic. So schematic is we use staggered lines, yeah, to show the roots and the cracks. And again, I want you to think about pros and cons, yeah, of this type of drawing. Why do we do that? And think about it. And of course, so this is an example of your schematic, way of drawing. And this one is detailed, it looks very much like the outside actual thing. And here schematic is different because we're drawing with the stagger lines. Where are the stagger lines? See that? So these are all the stagger lines. Different from the detailed drawing. See? Very different way of drawing the internal and external threads. See? For the same screw right here. So your pitch is here, your thread length, chamfer, minor, major diameters, and then of course this is your view, your front view, yeah. And then if you take this as a front view, then that would be your side view, okay? So it depends on how you look at it. You should be mastering all of your 6 views by now. And then of course your major and minor. Now we're going to turn this as a front view, and this one becomes side view. Yeah. So it depends on whichever way you want to do it. Of course, so this is your internal threads right there, and we're using the stagger lines instead of the actual approximation that we do in our drawing. Okay. And then of course, so let's go into the simplified representation. Is different. So that's the last way of drawing. We're going to use the visible hidden lines in our drawings to show the major and the minor diameters. Yeah. Again, your exercise is to think about your pros and cons for that type of representation. Doesn't have to be correct. Yeah, I want to know what you think. So just think. You have a freedom to speak and also freedom to think. And you have a freedom to write whatever you think. Whether it's so ridiculous, it's fine too. Just write what you think, okay? Okay, so let's take a look at how different they are. So here's a simplified version of drawing. And we're showing the minor and then their major diameter, your chamfers right here, your thread length right there. Yeah, it's going to start from there all the way to here. Chamfer is good for easy engagement. And here, there's a section view for the inner cut. And of course, this is right side view if we take this as a front view. And see like how different, 3 different ways of drawing the same thing, yeah? Detailed, schematic, with the stagger lines. And of course, here we use a visible and hidden lines to show the minor and the major, yeah? Diameters. So you gotta know the differences. But your exercise is not on the differences. You have to think about the pros and cons of that. Yeah, so give me what you think. I'll give you the exercise at the end of this lecture. This is just to show you a couple of examples, yeah, here and here. So you can be able to see the major, the top drill here, using the visible, yeah, and hidden lines. So you can see, okay, the diagrams. The pitch is shown right there, thread length, the chamfer right here, yeah. Actually the space, the internal space of it, right there, okay. That's a section view, yeah. And here is your front view showing you the major and the top drill on diameter right there. Okay, so we're done with the representations, 3 different types. So. Okay, so for drawing, of course, we're gonna use the tables, yeah, because it's important for us to be able to use a common language and common symbols and common values. So you go to the back of your textbook, okay, and go to the thread tables, yeah, and you can get all these values for the pitch, minor, diameter, top drill, diameter. To draw your screw threads, okay? You can just draw like whatever you want to do, yeah? You have to do according to what everybody else is doing all over the world. So we keep, that standard and go to the appendix to get these values. So what values are we looking up? We're looking up what we need to draw. Pitch, diameter, and the drill diameter, yeah? Very important. If you don't have your thread table access or whatever, yeah, you can use the minor diameter got to be, about 75% of your major diameter. Okay, meaning if your diameter is 100, then you can do the minor diameter as a 75%. Okay, so about give about 25% gap in between them. So you might think like it's a very big gap. It isn't like that. Okay, so when you go with the millimeters or inches, screw is a very small thing. Yeah, so the major and minor diameter about 25% is not that big. Okay. I want you to familiarize your brain with the sizes that you're dealing with. Okay, I don't know why the students have issue dealing with the sizes. Okay, so don't just stick with the human size. So you gotta be able to at the level of the things that you're dealing with. Okay, so use your intelligence to think at different levels: human level, material level, inside of the material level, atomic level. Your intelligence gotta go within. Okay, so that way you can understand them properly. All right, then we'll get into unified. Okay, that's thread form, the very first one, and of course, in drawing, we've got to write the notes. Yeah, thread note to define the thread that you're drawing. So what are we showing in a thread note? We're talking about the size and then the form. Yeah, the form of that thread. So it's kind of like giving the information to the machine people on the shop floor, so they can manufacture it. So anyway, the thread note, yeah, we use all the symbols and the values. Looks like that. So here you can, a big picture is you can be able to get how we write it. Yeah, space dash space. Okay, information, and then space. Don't forget space dash space and then information. Yeah. So we have 1, 2, 3, 4 groups right in there in a thread note. So let's see what we're talking about, each one of them. Alright, so the very first one is a major diameter, and that's your largest. Again, this is just the same definition. Major, so therefore largest. Diameter, threads per inch. So we are counting the number of threads every inch. Okay? And mathematically, we can get it 1 divided by pitch. Okay, you know what the pitch is. Don't confuse pitch with the pitch diameter. Okay, pitch diameters are diameters. Pitch is pitch. Very different. Okay. Then the form. What kind of form are we going to do? Thread form series. So you have UNC, UNF, and UNEF. C, okay, for coarse. F for fine. UN is we're in the unified. Yeah. N is for national, meaning like the whole country. We use the same thing, standard. Okay, so here unified, national, coarse, fine. Okay, E is for extra, so therefore extra. F is extra fine. And we'll take a look at the use. Coarse doesn't really need to do any kind of special thing, so just for general use. Fine, when it comes to the high degree of tightness that you want, you're going to use a fine, extra fine. Yeah. If you have like your engagement length is limited, then you're going to use your extra fine, like your sheet metal. Yeah. You can't use a coarse with a sheet metal, you're gonna have issue. Yeah, especially your roof. You can't use the adhesive or welding too much because one of them is ripped and the whole thing will come off if you use the permanent mating. Yeah, so yes, try to think of the mechanical aspects of it as well. So anyway, for drawing, you don't need it. Yeah, it's easier, just concentrate in your drafting. Then in your note, thread note, you also have to define your thread class. So thread class is the closeness of fit between the two mating threaded parts. Okay, you have 3 of them. One is a generous tolerance for quick assembly and disassembly. Then you have normal production for 2, and that's what we use all the time, yeah, if nothing has been stated. And the third one is your high accuracy, yeah. So it depends on the situation, you're going to choose the right thread class. We already knew that A is for external and B is for internal thread, okay? To identify that in your thread node. Then we have right-handed or left-handed. You know that right-handed is clockwise, and then your left-handed is counterclockwise, yeah? If you're not given a left-handed, then we assume it's right-handed, yeah, automatically. I don't know why. I think we produce a right-handed more than the left-handed ones. Okay, depth. So that's another thing that you have to define, yeah, in your thread node. So the depth is the thread depth. We usually put it at the end of it, and it's going to show you the depth for your internal threads, okay? And don't confuse the depth of your thread with the top drill, alright? Depth. You have different kinds of depth. So make sure you understand, yeah, the differences between these depths. Okay, here's a 2 different example, yeah. So the very first one is showing you with a diagram, and here is your thread node. Your major diagram, major diameter, and then you have your thread depth, right here, with this guy, yeah. Followed by your threads per inch, thread form and series, and this is fine. Thread class, you have 3 distinct, yeah. And then you have right here external and internal, and then this is your right and left hand. Okay, you can remember from here to here very easily, okay? And I don't know why every student have issue for the first 2. So first, you don't forget, the very first one is your diameter, and the second one is a number, okay, number of threads per inch. I don't know why you always have issue, okay, and you give me this as a diameter. Actually, diameter is right here, yeah, and that's just a depth right there symbol. So you know that the value followed by the depth symbol is the depth of your thread. Okay, so concentrate when you study to get this the 2 here. From here to here, you always remember. I don't know why. And maybe sometimes you forget this thread class. You know, thread class is only 3 in there for you. Second one is a general use, yeah, the standard one, normal one. So anyway, so another example, we also write just like that without the diagram, okay? The same thing, of course, your diameter, your threads per inch. This is your thread form and series. Here is your 1, 2, 3 thread class. Here is your A and B, external or internal. And then here is your left and right. Okay, pretty easy. Alright, so let's go and do the example. Yeah. So example here is given to you, and we have to identify what they are. So we have already studied, yeah, previous slide, and we know that this one is your major diameter, and then threads per inch is there, and then thread form and series, and then we have a thread class followed by external or internal. A is your external, B is your internal, R and L is your right and left hand. Okay. So you have everything and put that in. Don't forget the space and stuff, and don't forget to write in the way she wrote it in her textbook. So you're gonna get the correct without frustration here. Okay, then let's go into the next one. Standard, we're gonna follow ASME B1. Okay, so go all the way to the back of your book, and there's Appendix B. So we're gonna do for this chapter B, okay, Appendix B, all the tables right in there. So what are we looking at? We're looking at the major diameter threads per inch, and then we are going to look at the minor diameter top drill size, everything, okay, written according to the size, okay, of your fasteners. Okay, so the very first one, and we have to write down what this is about. So when you take a look at it, okay, since it is, I believe, in the question. Okay, so in the question is number 10, all right, number 10, find is the thread that you've got to write, the thread note 4. So since it is 10, we're going to write down the diameter is 10. So when you write in 10, or 12, or 11, or 8, or whatever, and you see the number, right, a sign right there, a little pound sign right there, you know that that is your diameter, yeah? And then of course you will go to the table and go to the number 10 in the table, yeah, in the appendix B, and you're gonna find that 32 is the threads, all right, per inch, meaning like in 1 inch there are 33 threads, okay, number of threads in number 10, yes, a screw right in there, yeah. And of course find we're going to represent with a UNF. That's a unified, because we are dealing with a unified method of the thread node, and threads per inch is 32 for this. I get this from the table in the appendix B, okay? And then this is your fine, and then of course this is UNF, yeah, for the fine screw. So that's how we write it, and you submit it, and you should get correct, yeah? Okay. And then we'll go to the next one, the same thing, we'll use appendix, yeah? ASME, go all the way to the back of your textbook, go to the appendix B, all the tables in the appendix B. We're going to use it depends on, depends on the questions. So the question is the same here. So the question is the same thing for the number 10, all right? Find, which is this guy, thread. But this time, they want it in the question. Read very carefully. Don't do like I do. I'm too fast, right? Because I do this all the time. So therefore, I'm getting it really fast. So here, anyways, inches, yeah. So therefore, we'll go to the inch table and then look for the number 10. And you're gonna get the major diameter is equal to 0.1900, right? This is in inch unit, and that one is in metric millimeters, okay? That's a very different thing. Okay, so we will change that into the major diameter, yeah, and then the minor diameter is also coming from the same table, yeah, ASMEB1, go there, and you will get both of them very easily. Minor diameter, you will have to use a major diameter and then calculate it, okay, it's on the same table. At the top of the table, it's going to give you the formula how to calculate the minor diameter, okay? Round it to the 3 decimal because you want it in 3 decimal, otherwise it's going to be showing incorrect for the same thing. So you will cut it out at the third, all right, decimal right there, 156. Then we'll come into matrix system. So let's see how we do the note, thread note. The same thing, you draw it, and then you're going to identify the size and threads in your thread note, yeah? So a big picture, it looks like this, okay? So then we'll get into details of it. Of course, start with the form, is your metric form. Metric form, we use the M, yeah, before the major diameter, so you know that you're in metric. Without the M, you're in inches, and the major diameter is your largest diameter, and your pitch is going to be millimeters per thread. Then tolerance clause. Here the note is a little bit different from our unified system, because see like how we write with the H's right there. So what that means is that's your tolerance clause. Okay, so when you see this H and G, we know that you are dealing with the tolerance clause. So talking about tolerance means space, so therefore looseness or tightness of the fit between the internal and your external threads, all right? Because your external thread is going to go into the internal thread to fit to each other, and there is space in between them, yeah? Like your shell in the whole system, your screw and the hole of the screw, the hole that the screw will go in has space in between them, yeah? So we deal with the looseness and tightness in between them, and we call that the tolerance clause. All right, so we have two classes, yeah, in the matrix system or matrix fit, and we use the H and G or HH or GG, yeah. So G, 6H and 6G is your general purpose. So the tolerance clause is 6H and 6G, right? Meaning like we don't have any other specifically defined stuff to think about it, so just go general. And C, second one is your 6H, and then 5G, 6G, is talking about a little more closer fit. Okay, what fit are we talking about? We're talking about the looseness or tightness of the fit between the internal and external threads. Okay, and we have tolerance grade. And then tolerance grade, it's just a number or a value. So when you take a look at these numbers, and if you see smaller numbers, you know that you're in a tighter fit. Okay, tolerance position is in letter, not number, letters. Okay, and it's going to show you two things. So one is the uppercase and the other one is the lowercase, right? Uppercase, we're talking about our internal, right, threads. In the lowercase, we're talking about the external threads. Yeah, you won't get everything in your head right away. Yeah, it takes some time for repetition. Yeah, repetition meaning like experience in your work to be able to get all of them by heart. So the first semester is always, if these are so new to you, it would be a little bit difficult for you to be able to get all of them. Yeah. So I totally recommend you to start to make your own. We call it cheat sheet, and it's just a common word meaning like the formal word is make your own notes. Yeah, to be able to get them in handy. Yeah. So you know how to take the quizzes and tests. And of course, application classes are a little bit easier, for the students to be able to take the tests and quizzes because they're all open book anyway. Because you need to know how to actually use the application, and you'll be spending time to be able to do that. So 3.5 months is not very long for a student to be able to get this skill. Yeah, so make sure you organize your notes and write down everything that you need to know. Yeah, because you won't have time to, even if it's open book, you won't have time to go back to each of the handouts. Yeah, it's a lot. So it's better to take all the important notes out and make it handy. Okay, and this is the same thing. Your right hand, left hand. So I don't have to talk about this again. You dab of the thread with this a little dab symbol. Of course, some students have an issue. Why it's the text we're talking about. It is at the end of the thread. No, but all I see is right at the front, right? Um, Actually, it's right here. Yeah. So we call it at the end of the thread node because you start from here and go all the way to here. So instead of putting it right there, we put it down like the second line to it. Okay, so it's kind of like looks like it's at the front, right, of the node. So it's just a matter of writing is a little bit different. So anyway, so you kind of get it, and then of course don't take it so tightly. Okay, uh, have some flexibility, in your way of thinking, because like I say, school academic world is very ideal. Everything that we do is so perfect. Mostly, and of course the outside world is the opposite of the academic world. Outside world is a very chaotic world with so many people, with so many different kinds of stuff going on. So when they write it, also, it come out pretty. Yes, and not. We have so much imperfections in the real world, and you have to deal with that, and you will get frustration out of it when you work. But just don't worry too much about it. It's just life. And if you don't see everything that is exact, forgive, and then try to translate it back to how you understand. Okay, you gotta learn how to do that skill, by the way. These skills are not listed in the human resources pages for job description. They are common sense. Okay, common sense to deal with the people, because human factors are not listed in the job description, but the human factors are the one that is going to get you in or out of the job. Okay, so dealing with the emotions of the people who you work with is very difficult thing. Sometimes I can do that. Not so many people. Sometimes we can do, sometimes we cannot do. Depends on the type of the people you deal with. And yes, there will be friction, there will be good things too, I want you to grow up and to be able to get these things, okay? um Sometimes you might get hurt, like in class I told you about it, don't feel bad about it. Just know that these things can happen to you in life, and you have to have a backup plan to pick yourself back out, okay, quickly. I think I have seen many students, so I come to know that some of the students cannot be able to do that. Okay, so that's because you're too young, and you are struggling to get that skill. So if you get hurt, you have to pick yourself back up quickly. Okay, and from now try to train yourself, train your mind, okay, train yourself how to do that, okay, so you won't go into depression. uh, yes, yes, a sight, and also you can be able to take life, as easy as possible. Life is just a passing thing, so don't fix yourself in it, just pass with it, okay, pass with it, and all the people will come in and out of your life. Yeah, let them come in and let them go out when they want to go out. Yeah. Um, Sometimes when they go out in many different ways. Yeah. Some people go out nicely, some people go out not nicely. Yes, some people go out very sadly or tragically even. We all have to accept it as it comes. Yeah. So I'm teaching all of my students, doesn't matter how old you are, to be okay with that. And it isn't easy, not easy for me too, not easy for other professor. We are, sometimes we got it and sometimes we don't, depends on the intensity of the event. But then because you're already in an educated field, that these things can happen, and when it happens to us, how are we going to take it gracefully, and how are we going to handle it wisely. And that's what education is about. We pay a lot of money to surround ourselves with educated people, because most of the educated people, they don't go crazy. They don't go chaotic. Of course, it's not perfect. Some of them will go very evil. Who knows, right? Evil people are also from the ordinary people. Genius are also from the ordinary people. Like I say, there are many different kinds of people. That you have to deal with when you go to work. So pay attention to that, and we will come back to here to our lecture. Yes, and the note, even the note writing note, is kind of like we always have to argue. Oh, this is saying like at the end of it, but no, the note is I'm seeing it right at the front. Yeah, things like that. So anyway, don't feel bad. Okay, it's just take it like as a second line. At the end. Okay, so now let's go into diagram example. So here you can see very clearly we are showing, see, the depth of the thread here. See, thread depth. That's supposed to be at here, but it's kind of like taking it at the end of the node, but we just put it right here. So anyway, so the very first one is your metric form M. So therefore that's a metric form, and you're not in the other system, which is unified. And then on major diameter, this is just a time. And then here is your pitch, followed by a tolerance class. In tolerance class, we have a pitch diameter, and we also have a minor diameter tolerance right there. And you have your big H, that's just going back to here. So I just want to show you here, and you don't forget the number and the letters. Uppercase internal, and the lowercase is going to be the external. So which is this guy, lowercase and uppercase, internal and external. So here you have uppercase, you're dealing with the external, and of course your right and your left hand, which is clockwise and counterclockwise, threads. Okay, then we'll get into not exercise. Okay, this is Oh, what is a pitch diameter? It's just a review. Yeah, pitch diameter. When you look at it from the side view, you're gonna see this surface. Yeah, and we know the major diameter and the minor diameter. Your pitch diameter is in between them. Yeah, because we're measuring with the line between the major and minor diameter, the center line between them, and then you're gonna measure that diameter from that side to this side circumference. Yeah. So here we are defining in a little bit different way, the one that we see in the beginning, yeah, with the center line between the major diameter and minor diameter. Here in this definition, we're stressing right here, yeah. So this is what the pitch diameter cuts. This pitch diameter is going to cut, yeah. The thread mean here, these are our threads. Yeah, it's going to cut the thread, is said. Yeah, at a point. Where is the point? They're cutting this line along that line, and that is the distance. Yeah, of the spaces equal distance from the thread. So here, okay, from here, they are all in equal distances. And again, I'll go back to the international students, so they would like translate right each word from English back to a language. And I do that too, yeah. Sometimes, because the English is our second or third language, or sometimes a fourth language to the international language speakers, because we have to go from country to country. So we kind of pick up languages, different languages very quickly, yeah. But then, of course, again, we have confusion inside of our brain because grammar is the backwards, yeah. It just a confusion right in the brain. So when you read it, also when you translate it, it's gonna alter the meaning of it. But don't worry about too much. Just write in a way you understand. But the major thing is like this line. Look at that. Okay, that's gotta be in between at the center. Yeah. From your major diameter is going to go from here, and the minor diameter is going to connect all of your roots. Major diameter is going to connect all of your crosses. That gotta stay in between them. Meaning like the center axis. So and that line again is going to cross all of your crosses and the root like your roots like that. Okay, that's what it's talking about. Yeah, the pitch diameter. So this diameter is going to cut the thread. Yeah, at a point where the distance of the spaces is going to equal the distance of your thread. Okay, so we're cutting like this, not horizontally like that, but vertically, because it said it so. See, the diameter, you can't get the diameter going from here to here. That's the length. Yeah, diameter is from here to here. So those are the things I'm trying to point out the students when we're reading the same sentence, but when we interpret, somehow you miss that major key point right there. So the cut is right here is straight in because you're cutting vertically, not horizontally. Okay. So the pitch diameter cuts the threads, cut it at the point, where the distance of the spaces is going to equal the distance of the thread. Okay, it's a little bit hard for you to be able to get it, but if you have a screw or something, you will look at it from this point and see the diameter, and imagine that you cut it. You can do it in SolidWorks or AutoCAD too. Cut it, and you will see that these are the same thing. Okay. Pay attention to these little things that you can miss. So when you read it, most of the students think going horizontally cut. Okay, it's different. So anyway, we're talking about vertical cut and talking about up and down here. Because when you go up, you see this part is called, okay, that part is called the thread, and this part is called the space, and that's equal. Okay, so I should draw that for you. Okay, and so that way you can be able to see it. So we're talking about, okay, the same thing. So now I make it really, really big. So anyways, the mine is wiggly. So that's the major diameter, and then this is your minor diameter. Let's say this is straight, okay? And here, that's your exit. When you do the vertical cut, we're talking about that. Okay, this is called space. So that in this material is called the thread, and that material is the space. Okay, so I should, and this space and that is equal. That's what we're talking about. Okay, why? Because this is your axis, right? Axis between the major diameter and the minor. That's your minor diameter, okay? And then this is your major big M diameter. This is a little m, okay? Minor diameter. And here, and this is your pitch diameter. Of course, there's another one on this side. See that? This is called spaces and that is called thread, okay? So it's not the language, it's just how you understand the physical thing outside. Okay, it doesn't matter what language it is written, you should be able to understand it. Understanding has nothing to do with language. Okay, understanding has everything to do with intelligence, your intelligence. Okay, and you gotta when you are doing learning, yeah, you have to enhance that skill. You have to enhance your intelligence. Because your job coming to school is you are working your brain, you're working your intelligence. Yeah. So even if you read just a simple one sentence, you have to think with it. You have to think with it. Okay, not just reading, but actually getting it. Yeah. Don't interpret in the way you want to interpret it, but interpret as it is given to you. In science, engineering, technology, mathematics, we gotta take it as we're given, okay? Not changing it to something else. The more you change something else, there goes all kinds of different interpretation and perception. Oh my gosh, you're gonna get a chunk of confusion right in there, and you will never come out of that confusion. Okay, so science is very simple, engineering very simple, technology very simple. If you take the things as is given to you without complicating it, okay, so don't complicate it, take it as it is. When it's a diameter cut, it is a diameter cut, and we cut it this way, that way, okay? So don't change the diameter cut into horizontal cut, okay? So if you don't do that, you will get it, yeah? And when you cannot understand, don't blame it on somebody else either. It has nothing to do with education, has nothing to do with language, okay? There's no language barrier. Language is nothing, it's just a description. But you gotta be able to understand what somebody is describing by using your intelligence, yeah? So then you can deal with any kind of people talking Chinese or talking Korean, talking English, Latin, okay, talking French, okay, French, talking German, okay, any kind of language, you should be able to make out of it, yeah? Alright, so let's go on to the exercise. Okay, so let's go on to the exercise. Oh yeah, so this exercise, you're given this note, yeah, and we gotta interpret. So your M is a metric form, 10 is your major diameter, 1.5 is your pitch because it goes in a direction. Now we have our little capital and a little yes, uppercase and lowercase letter. We are in the lowercase, yeah. So therefore, you gotta identify that's internal and external stuff, yeah. I'm going to show you again. If you forget about it, here's the uppercase for internal and lowercase for external. Dealing with the lowercase, yeah. Here, okay. Go back to here if you forget about it. Yes. A little slide right here, yeah, to be able to connect what you have read. Lowercase is your external. So therefore, when you see the lowercase, which is different from the one that we just saw, yeah, we know that we're dealing with the external, yeah. Okay, so for each the pitch diameter tolerance, yeah, 6H is your crest because the very first one is the pitch and the second one is your crest value, yeah. And then we're dealing with the here, yeah, external. Why? Because this little letter is a lowercase, okay? And then RH is your right-handed because it's going, yeah, your thread is going in a clockwise direction. Yeah, put them in Don't write whatever you want to write. Write it as it is given, and you will get it correct. If you write something else in the way you think, it's going to give you incorrect right there, and you'll get frustrated. I am giving this to you, so that way you know what to put in. Yeah. Last semester I gotta go over this. Oh my gosh. I give them homework and they don't know how to write, and it just go, for example, like they write yes or different things, it won't come out correct here. So anyway, so I get just give that to you, so you know you won't get frustrated this semester. Okay. All right. So thread tables for the matrix. So for the thread tables, you will go all the way to the back of your textbook. Okay, go to Appendix B, and you're gonna see them. Okay, don't worry about B1.1 and things like that. This is from the original table from ASME. So you have a little bit of a different. Yes. I would just say go all the way to Appendix B, and you have several tables right in there, and read the title of that in order to get what you want to get. Okay, title of that. Don't get confused either. Just go slowly and read the title very carefully, and don't get frustrated. Read very, very, very carefully to be able to look for the value you want. Okay. Depends on the type of the fastener, if that's a screw or a bolt or a nut or what is it. You identify that first before you dive in. Okay. Some students don't know what they're looking at, so in order for you to know what you're looking at, you go slow. Okay, just slow, and our eyes can go really fast. So eyes and brain has a gap. All right, so whatever eye is looking, brain is not catching. Sometimes brain is going before the eyes, so things can happen really quick in that process. So therefore you gotta slow down your eye, look at it, read very carefully, and relay what you see to your brain slowly. Okay, so then you can catch all of it. So don't worry about it. Don't go and find B1.1. I don't know where is it. I don't find this table wherever I get. Panic attack. They're all in B. What are you looking for? Are you looking for the major diameter? Depends on what kind of threads and what kind of type of thread. Okay, form of thread that you're dealing with. Okay. And you have to look carefully to be able to find them. Yeah. Okay. Then I gotta tell them like that, because it's just students are funny. Like they're always like fixing the instruction and the real thing outside. Instruction doesn't really work, because what's been instructed in the textbook doesn't really work in the real life. So don't depend on the instruction too much. Depend on yourself. Depends on your senses, because we can give you the environment that you will be dealing with at the work in the academic world. It's impossible to ask that from us. Okay, you will only get textbook. Textbook and the real world are totally different thing. Textbook doesn't exist in the real world. Textbook is just going to give you the knowledge, all right, what you need to know about that subject, minus the real environment outside. Okay, so what the student asks for, some of the student, not all, ask for doesn't exist in the school. You're asking for something that doesn't exist at the academic world. Give me the real world example, because the real world example comes with many different things, like different environment, different people. Who knows who is working there? We can't say that just one thing. There are so many things going on even at their own work, which never stay the same. So you might be having a group of people working this year. You might have a next group of people working next year. So even at the same company, you have a different results. So you gotta know these things. So we can't just give you one rule like that at school. You will only have a general knowledge of it, and you're gonna take it and make use of it to fit into the environment you will be in. Okay. Now you have to learn that skill, how to apply. We call it application. Academic will give you knowledge and method and systems, but how are you going to apply all of that you get in the real world is on your own. Okay, And if you suck, then if you suck, then you suck. Yeah, there's nothing you can do about it. And what you can do is you gotta train yourself to get that skill somehow with different environments. Okay, uh, please deal with that. Um, okay, so I'm okay with the instruction and things like that, but I come to realize that we gotta teach chaotically to fit the chaotic world. Because if you teach it so perfectly, students are accustomed to that perfection. And when they get out of school, there goes an A student can't make money, yeah, like that, because they have no idea how to survive in the chaotic world. So don't worry about the instruction, okay, being all identified to you perfectly. I do it intentionally. So you get that. You get that. And the most important skill you have to get is to figure it out by yourself. Okay? To figure it out. Imitating the example of the professor doesn't work in the real world. You have to learn how to do it by yourself. Okay, I will never reduce you any kind of grade for making minor mistakes. All right, I don't care, but I care that you struggle and try to make something happen. That's the most important skill you need, more than the knowledge, by the way, when you go to work. Okay, and then of course deal with the different people. Nowadays, even worse. You have to deal with different people, different. Oh my gosh, different races, different background. Some people are so rich, some people are so poor, some people are in the middle, yada yada. Okay, so you gotta deal with all of that environment. So it's so stressful. We age like really fast, by the way. We will be all like old like in 10 years working in that kind of environment. By the way, I hate to tell you that. So yeah, when you get the job, to make the most use of it. Okay, because the world is too much, very stressful. I don't blame some of the students can't stand it. It just I can't stand. Okay, sometimes either. It just you want to get out of it. But then you think, oh, we're like in the prison anyway in this world. We're born into it without asking for it. Here we are alive. So we just have to deal with what we've got. So anyways, so go back to the table. So don't look for the like rigid thing. Don't be rigid. Be flexible. And you know that ASME, when you read it again, there's a little word right there. ASME, I'm dealing with the ASME standard, and this is actually with 2001 and all kinds of stuff. When you go to the appendix down there, you have a similar table, but then of course depends on the author, whatever they're changing it, the way that they write it. And it's not only the author for, there is a whole bunch of editors who are right in between the publisher, and they're all working together. And here we go. There's a real world in the textbook. So whatever that we are perfectly doing isn't exist even in the textbook. So that's why you can find. You may be looking for like B1.13, depends on last year. Last semester. So no, just go to B1. And this is just talking about the 13M 2001, which is a revision. I think the author just copy and pasted from the rear table from ASME documents. So anyway, try to learn how to be flexible. Okay, is important. So when you go to the table, don't get frustrated. Give a little space. All you need is to look for the information that you want in all of the B tables. Look for it, okay, and read slowly and carefully. Okay, then we're gonna come into here to the exercise, and that's your matrix thread notes. So it tells you, okay, to go ahead and write the matrix thread note for the diameter 16, and we're dealing with the internal, so your uppercase and lowercase, okay, that you've got to deal with, and then of course a matrix thread, and we're gonna write and fill up this information. So first thing you gotta find is the pitch. We will go to our ASME table B and look for the thread. Okay, we're dealing with the thread. It doesn't identify whether that's a bold, so I just go with your general thing. Okay. Then when you go there, go look for the diameter 16. So that's your major diameter is given to you 16 matrix. So therefore you will go into the M table, M16, and you will see the pitch is going to be 2. yeah. The tap drill size is going to be 14. It's in the table, yeah. As soon as you get there, you will find it. When you look for, what are you looking for? You're looking for the major diameter 16. When you find the major diameter 16, which is M, because you're not in unify, you're in matrix, so go look for M16, and you will see all of that. Okay, write that down. Minor diameter, you always have to calculate, and the formula is given to you at the top of the table. Yeah, use that formula and put it in, and you will get 13 point. And she wanted in 3 decimals, so give it 3 decimal and put it in, and you will get correct. If you're putting a round or calculating the minor diameter wrong, it won't come out. Yeah, so check with what I have already calculated for you. 1.5, also 14.5 will come yes, from your table. Okay, do the same thing for the minor diameter, calculate it, and you're gonna get the correct, okay, value in it. So between the pitch 2 and 1.5, yeah, we want to know which one is finer. So the lower the pitch, the finer the thread is, so therefore 1.5 is, okay. And another question is, oh, go ahead and write a note for 16, yeah, because it says so here, millimeter, because that is a diameter, yeah, so 16 millimeter diameter, and it's got to be coarse, all right, on thread. So therefore, we're gonna write it M 16 times. Coarse is 2 because you're given 2 of them, yeah. So the very first one is coarse, the other one is fine thread, okay, for the same 16 millimeter. While we're having 2 pitches, because the first one is coarse and the second one is fine. This is finer because this is coarser, because 2 is bigger than 1.5, yeah. And here in this question, they want a coarse, so therefore we'll have to use 2 as a pitch right there instead of 1.5, yeah, that's it. Okay, how are we gonna draw the bolt? So we will go back to our basic drawing, yeah, and don't forget our extension lines right there. So first you can start with the bolt and then draw it, and you have your diameter and you have the angle, yeah, and this one is another angle right there for the 60. Just make it 60 from the center line, yeah, and that is 60 is because the end of your bolt head got to be on there, yeah, between 0 all the way to 60 degree. From here all the way to here, that got to hit the center line, and you are going to make, so you can start with the angle and then go there, draw the head and draw the diameter of your, okay, bolt, and then extension, and then draw your the top view, okay. So here is your bolt head, okay. From here to here is a 2 by 3 times your diameter, which is this guy, yeah. And here, of course, from here, that's from the top view, so you can see it from the front view. You're gonna have from here to here is gonna be 1.5 times your diameter, yeah, how wide the head is. This one is how tall the head is, okay. And we are calculating with the value of the diameter, yeah, from here to here of this rod of that bolt. So here, that is your bolt, and this one, even though we draw the top, okay, the top, which is the top this bolt right there, we can also use as a nut because this got to go into this anyway, yes, because bolt and nut, they fit each other. So anyways, let's go down to clearance holes. Clearance holes are very important, by the way, for the fit issue and fit purposes. In the real world, we have 2 parts, because we usually fasten by using the bolts, right, and the clearance holes to join the 2 parts in mating, yeah. So the clearance hole is going to allow this bolt, all right, to be attached to this material, to that material. We know that you're dealing with the 2 materials, 2 parts, because of the cross sections right there, yeah, the section view. You know that this is one material and that is one material. I would say part, yeah, different part. The material is the same thing anyway. By looking at the section types of lines, you know what that is. Okay, we are in the cast iron here. So anyways, you have a two different, yeah, part one here and two here, and this is a joining the two, yeah, mating. So here is your clearance hole, and then you also have another threaded hole right there. The threaded hole is where your thread is going to go straight in, and here's the space that we leave. Okay, and here you can see there's a little white, yeah, in between, yeah, and that is your clearance hole. So that depends on your major, yeah, diameter of your fastener right there, and also the type of fit. Is it normal, is it closed, or is it loose? Yeah, loose. These are all defining the space in between them. Again, we're going to consult with the appendix way in the back, usually B, yeah, B appendix. Alright, bolt and screw, sometimes you're going to do the counter, yeah, counter bore. So here, when you look at it, this clearance holes is your counter bore, yeah. So you will put your fastener right into that space right in there, and we call that the counter bore. It's very important to flush, yeah, with the surface, because you don't want this protruded outside like this example. Okay, let's go back to here. This is protruded. Here we use a counter bore, so it will go straight in what is in your head. Okay, it's will go into this counter bore space right there. Yeah. Another way is countersink, because they look a little bit different, yeah, in the for the head space, which is like countersink. See, it's kind of like a slanted or sloped or inclined, okay, surface right there for countersink. For counter bore, see, like kind of like a rectangular thing. So counter bores, we adjust the hole, right? You know, we design that type of hole, yeah, with this clearance hole, to recess the bolt and screw, yeah, heads below that surface. Yeah, here is your surface. We want it below. We want this to hide in the surface, so we do that kind of holes. Yeah. So mathematically, you have your CH is going to be, yeah, which is this head. See, this is where the counter bore space is. So therefore, your CH is equal to, yeah, your head is of course this little one from here to here, yeah, and then plus 1/16, all right, times 1.5 millimeter. Yeah, this is your equation right here. And then if you want from here to here for the head width, you can get it by adding, yeah, 1/8, about 3 millimeters to D1. Okay, D1 is the length of your head. C1 is the length of your clearance or hole, yeah, space width. So this is how we calculate CH and C1, which is the whole length and the height. Okay, this is the whole height, whole length, whole height. Use the height of the bolt at 1/16. The whole width, okay, from here to here. Use the width of the bolt, all right, plus 1/18. Oh, sorry, 1/8. Okay, plus 1/8. Okay, then you will get that. And countersink shape is a little bit different because you're dealing with the inclined surface right there, again below the surface, right? And you have a hole right there, and you have the width of the hole. You're going to calculate by adding, yeah, 1/8 again to the width of this bolt. Okay, so we call it the angle holes because it has an inclined slope like that. Yeah. Again, we used to recess a screw with the angle, yeah, held in there, so it's perfectly fit into that. So it's stronger, yeah, stronger to hold the materials together. Okay, then we come into the table. So here we'll have to write the nominal size, and then we'll have to write the clearance hole for that nominal size. So we have 1/4 and 3/4 go all the way to the back of your textbook, go to appendix B, and we're dealing with again with the clearance hole, so go to the clearance hole table, yeah, and look for this 1/4, you're gonna get this 9/32. Look for that 3/4, you're gonna get 13/16. Okay. Okay. So anyway, so a 3/4, and you're gonna get the 13/16. Okay. Alright, so again, that table is go all the way to the back, and you will see in the clearance hole table in Appendix B. Then we'll get into another nominal fit clearance hole. We want to get the the nominal both sizes for let me see. Oh, yes, it is the same question. I'm trying to find what the question is. So here, so the question is right here. Yeah, so you have a 5x16 and then 18. You're dealing with a course at UNC, socket, head, cap, screw. This is all we need. I should underline this one for you, okay? So that way you can, I'm gonna go ahead and highlight it for you right now. Yeah? Um, so this guy right there is the most actually, oops, changing color. Anyway, so this guy right there is the most important thing that you need for you to be able to write these things. Okay, so when you go to the table, you're gonna look for 5x16 is your major diameter. Okay, and you go in there and you are going to get the maximum head diameter, which is this. Okay, since she didn't write down here to 3 decimal place, you just give what you get from your calculator, yeah, and you will get that's correct. Yeah, if you just cut it out at the 3 decimal place like we always do, since she didn't mention here, the author didn't mention here, don't write it. Yeah, so this is how I try to teach my student how to do as yes, as it is defined, yeah, in there. Of course, you don't get like a word to word description here, but you have to use a common sense. The common sense is, hey, I'm not told to find the 3 decimal place, so therefore I'm just going to go as it is. Yeah, so then you will get the correct answer like that. And the maximum height of the head is 5x16, which is your diameter, major diameter. Anyway, so go to clearance hole diameter, and you're going to get 11 by 32. Go to the counter board, yeah, a table, and you're gonna get, just try to find a 5x16. You're gonna get 17 by 32. Go to the counter board table and get the depth. You're gonna get 3 by 8. Okay, and put everything all together, and you get all correct. That's just reading the table anyway. It will take some time for you to read it. So don't go fast like I do. Okay. Again, it takes some time. It takes about 10 minutes, you know, to read each one of them and find the right table. Again, they're not in the same table. They're in different tables in Appendix B. Yeah. Okay, then I will show you. Yeah. So here I copy and paste the table for you. 2 tables right there. So we are dealing with this guy. Yeah. So we come back into here, and you can be able to see, yeah, how we calculate each one of them. Yeah, 5x16. Yeah, and then of course the depth is going to be 11 by 32. Yeah, which is right here. Yeah, you can be able to see it. Yes, so because your question is 5x16 right there, so this is how we are getting, yeah, each one of them. And that is from the very first table. Yeah, since you're dealing with a 5x16, you have to multiply with 1.5, so that's a diameter times 1.5 is going to give you that. Yeah, because your A, yeah, this is your diameter. It's set so right here. It's set A 516. Yeah, so therefore you know that is the diameter here. Yeah, height of the head is equal to the diameter, so the same thing. Diameter times 1.5 is going to give you your max head diameter. Yeah, and then your normal clearance hole, go to normal clearance hole table and go and find 516, and you're going to get that. Okay, and this is how you calculate your counterboard depth, remember, and which is your is going to be greater than your head, yeah, which is h. So you add 1/16 in it because it's set so here. Yeah, so this one is not from the table. This is all from your counterboard calculation, yeah, from this little yes, I would say equation, yes. So don't forget these little equations like that, yeah. So that way you can be able to get all the calculation you need for this. See that? Okay. And the rest of them come from the table, yeah. I remember last semester one of the students couldn't be able to find how to do it and he got frustrated because this is not from the table because it started so like I say, the table, you look for the table, the title, yeah, name of the title. The name of the table is the title of the table, and that's where you're gonna look for these values. Yeah? So it's how you read it, okay? And that's what I try to say. Yeah, instructions are there. It's just that you don't know how to follow them. Yeah, my professor don't have to teach me. I like some of the students we don't have to teach so much. They know how what they're doing. Yeah, and they would just get that common sense out very easily. Some of the students just can't. You have to show them like um you can just say like go and read the table. They have no idea where to go. It's a very easy thing. It just the go with the name, right? The name. So if that's a head max max head diameter, that's what you're looking for in the table, yeah. Title, and you're dealing with the socket head cap screw. That's another thing you will look for it when you read the table because you can read other you cannot get the information for the screw from the bolt, can you? Cannot. But then you're dealing with the counter bore. Yeah, even though it is a screw, it will go into the counter bore. Counter bore is not a screw. Counter bore is not a bolt. Counter bore is not a nut. Counter bore is a hole. Yeah, HOLE, hole. So therefore you have to go to the whole table. Yes, which is your counter bore table. Yeah, see this kind of thing. This is just showing you the diameter. This is asking you the depth. So the only depth that's been given to you, yeah, is right here in the mathematical form, yeah. So when you study, you have to do these things, okay, and and that's what we said studying is, okay, to read, and don't just forget after reading it. Know what you are reading. Okay, so when you see this, hey, I can find it in the table. Where can I find? It's got to be in a formula. Yeah, it's got to get to your thinking. Yeah, so make sure you train your head to think. You have a very powerful brain inside. If you don't train it, it will go rusted. Okay, brain is again is a material. It needs to exercise, work only by thinking. Okay, things inside of your brain are very small. Okay, they're like a atomic size. So you gotta move them by thinking. Okay, like meditation. Meditation is a strenuous exercise of the movement of your brain by concentrating. Okay, concentrating inside of your body. Okay, inside of your mind. It's not just relaxing or it's no trying to sleep, not like that. Meditation is it's an exercise, yeah, exercise of your mind. You are constantly, your brain is concentrating at one point, okay, so you can get rid of everything else. It's not being your mind at peace. Actually you're working your mind aggressively, yeah, so thereby your brain gone, walking, exercising, yeah, keep it moving. So make sure you think. If you can't find in the table, I gotta spend about 2 minutes talking about it because that's what you're gonna do when you're gonna find the table. You're gonna say, I can't find this information in the where is it? Don't get panicked. Okay, the informations are given to you in the handout and in the table. Alright, so let's go to the next one, and here is the question. So you have M8, 1.25, and you're dealing with flat countersink is the hole. Alright, you're dealing with the screw again, yeah? So we go to the screw table in the appendix B and get the diameter, yeah? They're all the countersink, so go to the countersink table, go to the clearance hole table. You got all of that very easily. Yeah, so put it in 817.92 and then 8.4, and you will get all correct. All right. Next one is I show you where to go in order for us to get these calculation right there. It's not calculation, it's just reading. Yeah, so you are dealing with which is this guy 8, so therefore you go to the 8. Here you got all of that. So 17.92 right there. Head diameter. Now this is this. Okay, go to the next table. And go to 8 again. You get another one, which is your countersink, which is the whole diameter. This one is 8 because it's side is so it's a 8 is your diameter. So therefore you go put it in right there. Clearance hole diameter, another table. Go to here, go to here. You're gonna get right there. 8.4. It's not normal, it's not loose. Okay, it's close fit. Why is it close fit? Because it's set as whole. It needs to go through a piece of metal to screw into a plate. Here the clearance hole needs to be closed. Okay, so I'm gonna go ahead and highlight it for you. If you when you're reading, you're gonna miss it for some reason. I don't know why. So your highlights are from here to here. Yes, I'm gonna go ahead and highlight it for you. You're supposed to be doing this by yourself, by the way. I'm doing like it's like I'm teaching and then I'm studying like for you. You're gonna do these things by yourself. Either underline it or circle it, what you need. Okay, the rest of them is junk. We don't need. It's just close. So therefore, when you go here, you have no idea. I have 3. I don't know which one to put or not, and then put the whole thing and trying to do like correct and trying to find correct. Don't do that. You go straight to here because your problem set is so here. All right. So I'll show you how to study as well. So now, so this is the last one. So do we do we draw standard parts? So we don't draw standard parts. It's just we give the standard parts information like this. So you have a table like that for the standard part list table, and you're gonna see okay, please get these number 9, 10, 11, 12. So find number is how the parts located on assembly drawing, and then you have a quantity of these parts, so how many we need. So how many parts are needed in the assembly, and then you have your part or identification number for each one of them. It's pretty easy, and then the name, of course, and then the size and the series and material and the special requirement. Okay, these are just information, and you can be able to find them in the part list, whereas the part list is a table right up there in your canvas. Drawing canvas. These are the same thing anyway. Well, that's it for this chapter. Okay.